talks about the difference in two means. The big thing about this is we're going to have independent samples. So we're going to test hypothesis, claim for two population means. So for two population means. Now there's a big assumption in this section that's going to put it in contrast with the following section, section 9.3. And that is, we're going to assume independent samples. That is, first sample, the values you get for the first sample aren't going to be in any way related to what happens with the second sample. That's an important assumption, and that'll stand in contrast to the work we do in section 9.3. Now let's look through the requirements. I like to call them assumptions. Marty calls them requirements. The assumptions about this test. Typically speaking, we don't know the values of sigma 1 and sigma 2. What is sigma, anyways, for us in this course? Standard deviation. So we don't know the standard deviations of the populations that we're dealing with. Okay, that's fine. We're not going to assume that they're equal. If you can assume that they're equal, sometimes you get a more powerful test. That's okay. What else? We have independent samples. That's a key element of our assumption here. Simple random samples. Hopefully we do have simple random samples. That's not something we can test. And then either or both of these conditions are satisfied. The sample sizes are both greater than 30, which is ideal, or the samples come from populations having normal distributions. And we've tested that before. What are the ways we can test if something is a normally distributed or comes from a normally distributed population? What are some of the possibilities? Histogram. Ryan Joyner test, thank you. At most one outlier and the normal quantile plot. So there's a lot of ways you can test these assumptions. We're not going to spend our time testing these assumptions in this section just because it kind of slows us down. But these are the requirements, and once you leave this classroom, you should be spending a little time making sure that the requirements are satisfied. The big thing, though, is that they're independent samples. And we'll start with problem number 12. I should make one remark. With all these assumptions, you end up calculating a t-statistic. Now, the degrees of freedom in this t-statistic is either going to be the smaller of n1 minus 1 or n2 minus 1. There's a sample size from your first sample minus 1 or one less than the sample or number of data pieces or points in your second sample. That's one way to do it. It's a conservative way to do it. You can get a better estimate of the degrees of freedom for your t-distribution if you use this approximation. I think this is called the Satterthwaite's approximate degrees of freedom. It's a little bit messy, so it's certainly easier to do that, but it's more conservative. Okay, so let's do problem number 12. IQ and lead exposure. Dataset 7, IQ and lead in Appendix B lists full IQ scores for a random sample of subjects with low lead levels in their blood and another random sample of subjects with high lead levels in their blood. The statistics are summarized below. We're going to use a 5% significance level to test the claim that the mean IQ score of people with low blood lead levels is higher than the mean IQ score of people with high blood lead levels. So we'll do that. We'll follow it up with a confidence interval, and then we'll see what we can conclude based on that. So they give us some summary statistics. We'll use those. Let's start with a null and alternative hypothesis. So we're going to test the claim that the mean IQ score of people with low blood lead levels is higher than the mean IQ score of people with high blood lead levels. So let's highlight that here. Now Marty tends to write his null and alternative hypothesis with mu sub 1 is greater than mu sub 2. I like to be a little bit more descriptive with my parameters there. So let's start it out like this. The claim that we want to test is that the average IQ, that is mu, of people with low blood lead levels is greater than the average IQ of people with high blood lead levels. So that's the claim here that we're going to test. Remember that whenever you're testing a claim, that you need to put in parameters here. So I should see mu, sigma, or p. What I shouldn't see is x bar, s, or p hat. These are statistics. They don't belong in a hypothesis test in terms of the setting up HO and HA. As far as setting up HO and HA is concerned, where does my claim belong? The alternative, thank you. So mu sub LBL is greater than mu sub HBL. Nice. So what's that put in the null hypothesis then? Yeah, a less than or equal to. Mu sub LBL is less than or equal to mu sub HBL. Nice. All right, I didn't give you a handout for this one, but the steps involved here are the same as the steps we've done in the previous 4 sections like this. What's step 2 for us, typically speaking? Alpha. And alpha in this case is what? Thank you, 0.05. Step 3 for us has been replaced by, we're going to replace finding the statistic from the appropriate distribution with entering the data. Enter the data. And by that, I mean the summary statistics. So let's go back to the book. We have these summary statistics. So this is going to be my population 1. This will be population 2. I've got samples of both of these populations. Let's enter them into StatDisk. Hopefully you're signed on. Let's see, StatDisk, there we go. We're going to go to analysis. And then where? Thank you. Hypothesis testing. Mean 2 samples. And we're going to use summary statistics. Now, before I get lost in all these summary statistics, what form of the alternative hypothesis should I choose? 1, 2, or 3? Good. Mu sub 1 is greater than mu sub 2. Let's enter the statistics for our first population, our first sample. Our first sample, we had 78 individuals in this group with a mean IQ of 92.88 and a standard deviation was 15.34. Now what's nice here is that they give you an opportunity to enter sigma, but we don't know sigma. Typically we don't. You should be entering sample standard deviations, which is what we have here. If you look in the book, they say S equals 15.344. Let's continue with the second one. For the second one, we had sample size of 21, mean IQ of 86.9, and a standard deviation of 8.988, so-called 8.99. So are we okay here? Okay with all this information? Now when we do this test, the kind of alluded to this earlier, we're not going to assume that the standard deviations of both of our populations are equal. We're just going to say, you know what, they're probably different, and keep this one clicked as you work through these types of problems. We'll do evaluate, and there we go. What's the information that I need off of this screen here? The p-value. Good. The p-value is 0.01319. So let's write that down. So step 4, p-value is 0.01319. What's the p-value allow us to do now? Good. Reject H0. Thank you. Reject H0. What if alpha was 0.01? Would I be rejecting H0? No. But it's pretty close, but we wouldn't quite get to the rejection level. So the last step is to do what? Yeah, phrase it in words. Perfect. So for that, we're going to go to wording the conclusion. Might want to take a look back here. Which hypothesis held our original claim? HA. So that's our original claim. Let's keep that in mind as we look at our possibilities here for wording our conclusion. So if I number these A, B, C, and D, which branch should I branch to in order to state my conclusion? C. Good. Our hypothesis does not contain the condition of equality, so it's a no there. Did we reject it? Yes. So down here would be C. So start out by wording it, the sample data support the claim that, and then state that original claim in words. Someone want to give me their conclusion in words? Want to take a shot at what theirs says? Have it evaluated? Olivia? Beautiful. Beautiful. Sample data support the claim. So when I grade your exams, I want to see you start out the right way. Sample data support the claim that. It'd be nice to see the parameter that you're testing, and you had that, the mean IQ, and then a description of what that mean IQ reflects. The mean IQ of people with high blood lead levels or low blood levels is higher than that of people with high blood lead levels. So a couple different ways you can phrase that, but describe what you're testing. Describe what that hypothesis is. Well done. Any wrap-up or follow-up on problem number 12 here? Okay with that one? There's one thing that's kind of curious about this, and that is, let's see. One thing that's kind of curious about this is sometimes their confidence interval doesn't match here. So we did significance level of 5%, but it gave me a 90% confidence interval. And I think what they're doing is they're just coming up with one value for your test statistic. You know, you can see that here. And realistically, you should be splitting up your confidence interval into two parts to get a lower than and a less than. I think if I went, this is my alternative test with a 5% significance level, that it would give me a confidence interval that's 95%. Let's see that that's true. So yeah. So this doesn't always agree with our level of alpha here. That's a little frustrating. But if you needed to, just go back and do an analysis of, you know, the confidence interval. If you needed to get a confidence interval that matches your significance level, go back and just do it. All right? So there's nothing too onerous about putting in these values for your analysis in a confidence interval. You just do a confidence interval of, let's see, mean to independent samples is what you would do. Okay, let's try another one for confidence interval, or excuse me, not a confidence interval, but a hypothesis test of two population means. And that'd be problem number 18. Any other follow-up on problem number 12 here? Problem number 18 I kind of like because the author shows that he's quirky a little bit. And actually kind of almost boast of it. So when the author visited Dublin, Ireland, home of the Guinness Brewery employee William Gossett, who first developed the T distribution. Who told you about that? Okay, all right. I'll let you get back to me with that answer. He recorded ages of randomly selected passenger cars and randomly selected taxis. So imagine this. You're on vacation with the author. He's like, wait, honey, I got to catch this license plate. You know? And he does it again and again and again and again. All right. Self-admitted. There's no end of fun to traveling with the author. The ages and years are listed below. We might expect that taxis would be newer, so test the claim that the mean age of cars is greater than the mean age of taxis. So, okay. Let's start there. Let's start with that as the basis for our hypothesis test. What would you write down for HO and HA? Given that. Now, personally, I'll do some subscripts for this one like I did the last one. Maybe sub-car, sub-taxi, that, just so that we can see things and keep them straight. So problem number 18. What do you got? What are we going to write down for HO and HA? No one? Come on, make me look good. Yeah.
I said I used like the abbreviations of MAC is greater than MAT for HA.
Okay. So,
HO, I said MAC is less than or equal to MAT.
all right, so we need to use mu.
Oh, yeah.
All right. So mu sub car, and I think you got the directions right, which is good, is at most mu sub taxi. So the mean age of cars is at most the mean age of taxis. That's your null hypothesis. Of course, I probably should have started out with mu sub car is greater than mu sub taxi. That's the claim that you're testing. So that's our original claim. OC. Let's circle that. That goes in the alternative hypothesis, and then you figure out, all right, well, this must be what's in the null hypothesis. Step 2. I don't think they told us a value for alpha here, did they? No. So what should we use? Yeah, two values, 0.01, 0.05. I think I heard Will say 0.01, so we'll use 0.01, but I don't think it's going to make a difference. 3 is to enter the data. Now in a traditional class, step 3 would be to find the appropriate point on the t-distribution and set up your null and alternative hypothesis, or your reject and fail to reject regions based on that. For the previous problem, your two-tailed test here gives you critical regions that are to the left of 2.00414 and to the right of positive 2.0414. So anything to the right or to the left of those puts you in the rejection region. Now, the difficulty about this is you have to first find the degrees of freedom and then figure out, okay, well, you know, what's our test statistics. There's a lot of work that goes on in getting that. And it's just a lot friendlier to deal with a p-value. Let's see. One thing to note, they're using the approximate degrees of freedom given by that test. That's good to see. Typically, when I taught this class, I made it easy for my students. I said, all right, your degrees of freedom is going to be the smaller of n1 minus 1 or n2 minus 1. Since clearly it's not 77 or 21 or 20 for your degrees of freedom, they're obviously using the approximation. That's a lot of work. We're going to make our life a little bit easier. Step 3 is going to be enter the data. And because I want to have some time at the end of the day to discuss things for you or prepare you for your exam on Monday, I'm just going to give you the p-value. The p-value is going to allow us to do step 5. Based on our p-value, based on our value of alpha, what do we get for step 5? Reject H0 or fail to reject H0? I've heard both. Fail to reject. Good. This is much bigger than alpha. So, yeah, fail to reject. Let's state our conclusion in words then. Remember, I'm putting much more emphasis on this than what I used to because it used to be so much work just to get to your conclusion. But it's gotten a lot easier for us. Nope, wrong one. This one. So see if you can't work your way through to the right spot to word your conclusion. Someone want to give theirs a shot. What does yours look like? Cat? Perfect. Someone else want to try theirs? So, mine's pretty similar. There's not sufficient evidence to support the claim that in Dublin, the mean age of cars is greater than the mean age of taxis. Basically, what you're saying in words is that there's not enough evidence to support our original claim. Nice. Now, were we close to rejecting? I mean, if we got a little bit different data, do you think we'd be rejecting? Nah, we're far away from rejecting. So it didn't really matter what we chose here for alpha 0.01 or 0.05. We weren't even close. Now alpha, let me remind you, is the possibility of a type 1 error. What happens in a type 1 error? Yeah. H naught is true, but you reject it. So a type 1 error is to reject H naught when it's true. So reject a true H naught. What about a type 2 error? Yeah, fail to reject H naught when it is false. Okay. What I'd like us to do for this one is look at what a type 1 and a type 2 error are for this problem. H naught was that mu sub car is at most mu sub taxi is less than or equal to, and HA was that mu sub car is greater than mu sub taxi. Now, there's a lot of variety in ways you can state this, so might not be a bad idea to try and run yours by me. I'll take a couple examples and we'll look at them. But basically, I'm looking for two things when you do these types of problems. The first thing I'm looking for is what's actually true. And then I want to know what your decision was compared to what's true. So try working through this, figure out what a type 1 and a type 2 error is in words that relate to the problem. So I don't want to hear a definition. I will give you the definition. Like, here it is. You just have to know how to put it into words that come back and relate to this. So give that a shot, and then we'll compare some answers. Yeah, sorry about that. All right. I see a lot of well, blank faces. Let's take a look at this. The first one, a type 1 error. What you want to state is two things. You want to state what's true, and you also want to state what your decision was. So let's start with what's true. What's true in this case? No. No. The mean age of cars is at most the mean age of taxis. H0 is what's true, right? So let's state that in words. The mean age of cars is, now here I'd accept two things. You could say less than or equal to the mean age of taxis. I find it convenient to say is at most the mean age of taxis. So that's great. That's telling me what's true. Now let's talk about our decision. What do we decide? This is true, but then what happened? But the data reject that claim. We okay with that? So there's two things. You have to tell what's true and what your decision was. Both of them in words. I don't want to see people using H0 or mu, etc. You should be using words like a claim or words like mean, etc. But we shouldn't be using any symbols that are unique to this class. Something that somebody could understand independent of being in this class. Let's take a look at a type 2 error. Yeah, question? Yeah, please. Let's hear yours. Yes, that's another way of saying it. Reject this claim, the mean age of the car is less than or equal to the mean age of taxi, even though that claim is true. Perfectly valid. So there's a lot of different ways you can say this. I'll tell you this. I really hate grading this page when I grade your exams. Usually I try and do one page every 30 seconds. This time it slows me down to about 2 minutes or so because I really got to dig through. I'm like, okay, I got to think through exactly what you're saying because there's a lot of variety in how you can do this. So when you multiply it by 2 minutes times 30 tests times 2 classes, it takes forever to get this one graded. But I will grade them carefully, and if you disagree with it, then please talk to me and say, well, wait a minute, how come this is wrong? And I'll work through it with you. Type 2 error. Fail to reject H0 when it's false. So what's true in this case? Yeah, the alternative. So the alternative is true, but what did we decide? What was our conclusion? That H0 is true. We failed to reject H0 even though this is true. That's what a type 2 error is saying. So we just got to put that into words. I'll give you a few seconds to try and come up with something for yourself. Put into words the fact that this is true, but we didn't reject this. There's your type 2 error. Okay, does someone want to give it a shot? Rusty, thanks.
The mean age of cars is at most the mean age of taxis, but the data doesn't support that claim.
Your first sentence said that this is true. You said the mean age of cars is at most the mean age of taxis. So that's implying that this is true. But in a type 2 error, it's actually HA that's true. So it's true that the mean age of cars is greater than the mean age of taxis, but the data fail to support that claim. That'd be one way to say it. Does anyone else want to try theirs? I mean, it's better to learn now than to learn on Monday. Gio?
Mean age of cars is greater than the mean age of taxis. Data reject that claim.
Almost. The mean age of cars is greater than the mean age of taxis, but the data fail to support that claim, right? Because we didn't reject this claim, we failed to support it. So let's try it that way. The mean age of cars is greater than the mean age of taxis, but the data failed to support that claim. Well, fail to support would be something that you would see if you're looking at the alternative hypothesis. Fail to support means we can't reject H naught, means you fail to reject H naught. Yes? Meaning it's false. Yeah. So sure, it's a different way to say it. So a different way to say it, if you just wanted to keep with the perspective of H naught, would be the data fail to reject that the mean age of cars is less than or equal to the mean age of taxis, even though that claim is false. Yeah, that's perfectly fine. Because what you're saying is that this is false, but we failed to reject it. That means we concluded that this was true, even though it was false. So that's a different way to say it. And again, that's perfectly acceptable. That's why there's no cookie cutter example for, well, this is how you have to do it exactly. Because there's a lot of variety in how you could word it. But the spirit has to come through. That this is what's true, but that was our conclusion. So those are the two things I'm looking for together when I'm looking at a type 1 and a type 2 error. Any other comments or thoughts on that one? Now, I think there was some more work to do with this one, or that we can do. So let me take a look back here. No, there was with the last one. Let me do one last thing with this one. It goes a little bit beyond what we have to do, and that is let's look at a confidence interval for the difference in these two things. So, yeah, actually we got one right here. Down here. Let's try and understand something. Let's see. Is that the one I want? No, this is the wrong data set. All right. So let's put in this data set again. You know what? I don't want to put in the data set. I don't feel like typing in all those values. My bad. Let's look back at the first problem we did in this section, just to throw in a little bit more with that. So the first one here was that blood lead levels of, the IQ of people with low blood lead levels is higher than the people's IQ with high blood lead levels. So that's fine, we rejected that. But let's also look at a hypothesis test here based on that. Now, if I move this over from one side to the other, then I'll see something interesting about the difference in these two. When I subtract LBL minus mu HBL, the null hypothesis is going to include the possibility that this is 0. So when you look at your confidence interval for this on your statistics output, take a look at that confidence interval. Does it include the possibility that the difference could be 0? That there's no difference in the IQs of people with low blood levels and high blood levels? Is 0 in here? No. Should it be? The answer is no. Because what we said in our conclusion for problem number 12 was that there was a difference. And that means that 0 should not be in your confidence interval. If 0 is in your confidence interval, one of the possibilities is that mu1 equals mu2. In other words, the difference between them would be 0. Since that's not the case with our confidence interval, that goes along with our conclusion that we rejected H0. So it's nice to see that our confidence interval matches our conclusion based on our hypothesis test. Oops, wrong one. There. Anything else on hypothesis test for two population means in the independent case? Diamond? So when you're stating your conclusions for type 1 and type 2 errors, there's two things I'm going to be looking for. I'm going to be looking for you to state, first of all, what is true. So tell me what's true in your type 1 and your type 2 errors. And the second part of it is I'm going to state what was your decision. And I'll give you a little bit of a hint. Your decision should not match this. Why? If it did match this, you wouldn't be making an error, right? So it can't match this. Your decision has to be opposite of what's true. So you're going to start by stating, all right, here's what's true, but this is what we decided, or this is what the evidence helped us decide. So in the case of this last one, if you make a type 1 error, what's true? H0 is true. So you can start by saying, it's true that the average age of cars is at most the average age of taxis. That's what's true. But since you're making an error, what was your decision? But our decision said to reject that claim. That'd be one way to say it. Or you could say the data support this claim, which is saying, again, the same thing. You could either reject H0 or say we support HA. You know, in face of the fact that H0 is really what's true. And you do likewise for a type 2 error. Just roles get a little bit reversed. HO is false. So you start by saying something to the effect that HO is false. So, you know, the idea that the average age of cars is at most the average age of taxis is false, but we didn't reject it. So you failed to reject that claim. So again, stating two things. What's true and what your decision is. And hint, should be opposite of A. Okay. TJ?
So is fail to support a good way to do it? So I have the mean age of cars is greater than the mean age of taxis, but the data fails to support that claim. Is that correct?
Yeah, that'd be a different way to say it. So let me restate it here. The mean age of cars is greater than the mean age of taxis, so that's saying what's true, but the data fail to support that. Now, if we fail to support that, that means we didn't reject H0. We're stuck concluding that HO is true. So, yeah, that's a perfectly valid way to state that. Okay, for homework, try problems 1 through 21. That's section 9.2.